Welcome back. In this video, we'll start looking at ETL patterns which go beyond the functional context. Here, we'll start to look at the operational matters related to data itself. So, one of the first patterns that you'll start to consciously think about when you build your data pipelines is operational metadata. So, this asks the question: when you do data pipelines, when you do processing, transformations, etc., when did what kind of transformation happen? How long did that job run for, and what did it touch, etc. So, what did it populate, and who executed that particular job? Could be like an analyst, could be a developer, data engineer, whatever. So, the operational metadata refers to the trail that's necessary for you to collect in order to reason about how did a particular piece of information land up in that integrated layer. So if you go back to that example of that customer cost of customer acquisition, the problem that finance and business were debating about, right? And then the integrated layer solves the problem. And let's say at that point the answer comes out to be like 3,000 rupees, right? The finance person could agree with it, uh, but the business could say, "Look, I don't think this is right. Show me how did this come about." So then you would have to go back and prove that that particular value came about as a result of this pipeline of things that ran before it, right? And sometimes it's just a straightforward formula, and other times it's actually much more than that. So think about it. When you have a customer cost of acquisition being calculated as a formula, the formula needs inputs. The inputs are in the form of data. The data comes from various sources. The sources themselves are being ingested into the staging layer at their own frequencies based on what the source provides. Right? The tooling varies for each of this. The scheduling varies for each of this. The tasks required to be done have a set of dependencies which are required to be tracked. So the question that the business is asking is actually genuine, right? Are you not missing anything? Are you confident that this is complete and this is accurate? And that confidence not doesn't come just because you state it, right? It doesn't come just because one task ran completely. It comes because you have what's called as end-to-end traceability. You're able to trace the data all the way back to the source, all the way back to the raw information that came in the first place. That's what makes it extremely, um, you know, confidence building or trust building, right? And the way you go about doing that traceability is using this operational metadata that you also collect. So this is a very important aspect. All ETL patterns come for any kind of production use which is meaningful. You have to think about operational metadata. So it's one of those things where the analogy is to the world of software engineering. When somebody gets given a requirement and then they go about writing code for it, and then they say the code is ready, and then a senior developer comes in and takes a look and says, "Where is your error handling? Right? Are you that confident that there is no errors that can come into any of your input parameters? Uh, how confident are you that the exceptions that get thrown out as a result of some malformed behaviors or malformed datasets do not actually crash your program? Where is the logging? Where is the information that needs to be shared so that somebody else can assess what progress you've made as a software?" So those all become critical things that the trained developer knows that he or she has to make leeway for, but the rookie completely forgets about it, just looks at the problem statement at hand. But something similar is very common with data engineering, and those trained best practices that are necessary, one such as actually this operational metadata. The second thing that is really, really critical, and this is where I've seen so many projects fail, is the ability for you to build a pattern, or rather build an ETL, which incorporates this pattern of dealing with quality problems. Now, we spoke about the example where user ID 123 maps to two different users, and so how do you deal with it? You don't deal with it completely by yourself alone, right? So you need some help from the business domain typically. But what you don't want to do is actually reject data, because data loss, the moment there is this sense of data being lost from the OLAP system, the trust just plummets down. right? The rest of the business starts to doubt everything that you do. Because when you lose data intentionally, you've essentially made a call on a topic that is actually not of your concern, right? Typically, as a data engineer, as a data platform owner, the the way to interpret data is actually something that the business should take a call on. Right? The data platform is not best placed to actually take that call. So the example where the product is being sold, but the product reference doesn't exist, we have to, get that payment information in. Otherwise, finance will have a different number from what is reconciled from what is paid, right? So keep that in mind. The other angle here is, what does error handling look like? What does exception handling look like in this case? So we spoke about how software has exceptions, and we all know how to handle those exceptions. What does that look like in the world of data? Actually, it looks like something that's very similar, right? You have a bunch of assumptions you make about what data is supposed to be, and those assumptions are getting invalidated. As a result, is your code going to throw exceptions? And if that's the case, then you have to deal with it. So the classic example here would be you're computing average, and the average is computed based on, you're summing up a bunch of things, you're counting a bunch of things, and you explicitly using the formula, right? Sum divided by count. But then the entire operation happens only because, rather, happens on top of a source table which is getting filtered, and it so happens in that run, for that instance, for that execution, the filter filters everything out. So then the final answer that you're computing and you're inserting into the business table, you're just doing the average for that particular day. Because the business is expecting to see some value, and if there's generally no data that matches your criteria, you want to be able to say zero, right? You want to be able to say null. But if your code is going to blindly do like sum divided by count, and the filters actually filter out everything else, the count will actually be zero, right? So then that average code returns potentially um, division by zero error, and that's a SQL error. That error needs to be handled explicitly. If not, then that entire syntax, that entire statement is failed. Right? Sounds very similar to software. Yeah. So that's what I mean by rejections due to quality and error handling. You have to deal with all of this in a way that's carefully planned out. So the best way to deal with quality issues, the best way to deal with exceptions is to move on, right? Not be hampered by it, but log enough information for us to be able to go back and trace. So trace is everything. Like you need to be able to trace everything, right? Source is what we have as the source table. Target is our target table into which we are populating. So this arrow that you see here is the ETL that we're building. That ETL pattern has those patterns we spoke about in previous slides. But then it's very important you build the validation fail pipeline, that branch of the pipeline as well. And what does that branch do? For all validations that fail, that data gets logged automatically into target rejects. In some cases, you could also log it back to source rejects, but it's more common that you actually start to keep it as target rejects, so that then you can go back and take a look, and business gets exposed to the targets, the target rejects, and then they can take a call and say, okay, yeah, I need to include rejects or not. So what are the common examples here? Duplicates. Duplicates is such a common problem. Why is that the case? Because the way that source data is getting extracted and brought here could change based on what the nature of the source is. Sometimes the source might be giving the same data multiple times because you asked for it, or it lost track of what it gave you last time around. So when you asked it again, it gave from the previous time when you actually already successfully completely got the data in, or you just happen to be reprocessing the same file because your pipeline restarted in the middle for whatever reason. The machine failed and it crashed and came back up. Whatever, right? Multiple reasons. But the data could be present in duplicate, meaning the file is duplicated, present again, or the data within the file is duplicated because the source system had a glitch, whatever. So that duplicate data has to be handled. Now, there is a difference between duplicates which are full row, meaning they're exact copies of the entire data record is actually an exact copy of another data record we've already seen before. In which case, it's relatively easier to think about. You can just drop this duplicate row because you know for a fact that it already is with you. But even there are scenarios where it could be genuinely, possible that the entire row is coming again. So think about event sourcing. Event sourcing, we spoke about this paradigm in week three's lecture. Event sourcing captures the changes as separate events. CDC, change data capture, is one such example of an event sourcing paradigm. You could have the record of a particular table be changed to some other value and be changed back to its original value. So then if you take a look at those records will look as though the record that you see now is actually the exact same as the record that you saw the day before, but yesterday's record is actually different. So the notion of what is duplicate is actually very much a function of time, right? And very much a function of what's happened in between. So you have to be a little more nuanced about it. So the common patterns, let me again emphasize this, right? It's very common to see duplicates within a batch of processing because of like the source glitches, job restarts, and things like that. In which case, you just completely check for full row duplicates, and wherever there are full row duplicates, you can eliminate that. But it's also common that you have full row duplicates across time. In which case, you have to take a nuanced view and say, if there are changes to that data that happen in between, then these full row duplicates are genuine. Right? So how do I know there are changes that have happened to that data? You base it on primary key. So as an example, user ID, right? I've changed my email address. I've given my Gmail address, but after some time I decide to change my mind and bring it back to my Yahoo address. In which case, the sequence of change would go from Yahoo to Gmail to Yahoo again, and as a result, if I pick up the set of records that have been created in sequence for that user ID, I'll get the sequence exactly in order. And each change that has happened has a timestamp attached to it. And that timestamp is the operational time when that particular change happened. So therefore, it is not a full row duplicate. It is in fact a primary key duplicate. But that's perfectly fine, right? The business scenario allows for it. I do allow for changes to happen and changes to revert back to the older versions. So keep this in mind. The second type of rejections that could happen is metadata type checks. So what I mean by this is I'm expecting columns to be of certain type, let's say the date type for my date of birth column, and what I get is instead is an integer. So do I reject or do I fail? What do I do? So there are two ways to deal with it. One, you could just say I reject the entire row because the date of birth is invalid, therefore the entire row is invalid. That's okay, but in my view, that's being a bit draconian. Again, the mantra that we want to follow is as little data loss as possible, as little, in fact, no data loss ideally, and then you want to reject for as little number of reasons as possible. So the other way to deal with it is to say, if the date of birth column is important, then of course I put it into my rejects table. But if it's not, I could live with it. I could live with issues in the data, in that particular data column. So for a particular user, the date of birth came in as an integer. I could check and say, okay, yeah, this is wrong. I logged that information to the target rejects, but I also persist that information into the target table with the key change of, with the important change of the date of birth being replaced by a null value. Why do I replace with a null value? Because the value that was given to me is wrong. I don't want to reject the row. The rest of the fields make sense. The user ID, the username, etc. So I replace this with a null value, which is a default value, or maybe the default value is like the year 0000, whatever, right? Some way to to not violate the type of the column, and I allow that row to continue into the target table. With therefore the semantics being the business user who comes and takes a look at it, he comes and says that okay, look, whenever the values are something ridiculous, like this is null or the year 0000, obviously nobody has won them. I know for a fact that these were quality issues that were seen as part of the source, and the ETL fixed it for me so that I can get access to the rest of the columns. Right? So that's the way to deal with it. Um, there could be other kinds of constraints that are violated, like the primary key foreign key relationship would get violated. But we saw how to handle that already, right? That's with the reference value. Um, okay, so that's the second category. The third category is that there could be semantic quality issues. So, semantic business value checks could be taking place, and that results in quality um, invalidations. So, the example here is payment table itself. The payment amount can never be negative. At least the business scenario does not permit it. So, in that case, if I get a payment amount which is negative, what do I do with it? From a perspective of column type, negative values are still integers or floating points or decimal points. So the column type matches, so metadata type check goes through successfully, but the semantic check fails because the payment amount is negative. I could choose to do the same thing, right? Log the actual value in the regex table so that I can come back and take a look and trace it back. But log the quality controlled value. In this case, the quality control value could be null, could be zero, could be something else. Um, but that gets logged in the target. So that's the way you deal with these quality issues. Now, what you do then as a best practice is you get business to come back and take a look at projects. And what invariably business will do then is to say, look, some of these are source issues, go fix it at the source. Then you get the source guys and they start to look at the patterns in the rejects and figure out, yeah, okay, so these quality issues come in whenever these five things happen. And then they go back and fix it, and then they come back and give you the new sources of information, and then you start it again and so on. So that's how the system keeps improving over a period of time. The last thing that I want to talk about in the patterns section for operational matters is data lifecycle management. This is actually a very, very interesting topic by itself. So I'm going to just take a logical pause here and we'll pick it up in the next video.